So continuing with the description and explanation of various processes, the isothermal, the isochoric, isobaric and adiabatic processes. In the last lecture, I derived the equation for the work done in the isothermal process. W is equal to nRT log natural of V2 minus log natural of V2. Okay. Now, as I told you in the beginning, that equations speak and the physics starts after the derivations are obtained. So from this derivation we can see that nRT, they are all positive values. This is also a positive value, this may be a positive value. But it speaks that if this ln V2 is greater than ln V1, then this becomes positive. Otherwise, it is a negative value. So that's what I say, that if V2 is greater than V1, and that is the condition of an expansion, then this is greater than this one, and therefore W is greater than 0. What does that mean? Greater than 0 is this? Means it is positive. The gas absorbs heat and does work. Also in such a situation, the Q is equal to W. The heat is equal to the work done. Okay. If V2 is smaller than V1, on the contrary, there is compression. This is less than this, W is less than 0, and it's negative. Heat is released and work is done on the gas, that is the system, by the environment. So this is about the isothermal process, wherein we have taken PV is equal to nRT. Or P1 V1 is equal to P2 V2 is equal to Pn Vn is equal to a constant, and that is the statement of Boyle's law, which holds good. Now there is another process we are going to talk about, and that is the adiabatic process, which I have already discussed with you, wherein the system is insulated from surroundings and heat is absorbed, okay, or heat is released, and that is whether the heat is absorbed or whether it is released, it is equal to 0. So no heat is absorbed and no heat is released. Okay. Work done by the gas, what does it do? It decreases U. Not, I don't mean U. It decreases the internal energy of the system. So naturally, when the internal energy of the system decreases, then there is fall of temperature for an ideal gas. Now, for the adiabatic process, we will just take the equation in this form. For adiabatic process, PV power gamma, okay, this is Mr. Gamma Pahalwan, gamma, bulbule hind, gamma, okay, so gamma, PV power gamma is equal to a constant, where gamma is very simple. Gamma is defined as Cp upon Cv, it's a number more than 1. Sp upon Sv, which is the specific heat for per gram, per gram, or the capacity is heat capacity is Sp upon Sp. Okay, so Cp upon Cv, this upon this upon this, one and the same thing, and of course we'll see in the due course of time. We will not attempt to derive this equation Pv to the power gamma here, and maybe in chemistry they do it for you, because thermodynamics is a common thing between physics and the daughter of the physics, which is chemistry. I am saying so because earlier there used to be in several universities in Europe, there used not to be a department of chemistry, but the department used to be called Department of Physics and Chemistry. Okay, now of course physics is like this, but the daughter chemistry has become like this subject. So suppose I want to change from one state where the variables are P1 V1 to P2 V2. So I'll write therefore P1 V1 to the power gamma is equal to P2 V2 raised to the power gamma is equal to Pn Vn to the power of gamma is equal to a constant. So let's see what happens in the adiabatic process if we make a change of states P1 V1 T1 P2 V2 T2. What is the work done in the adiabatic change? The work done will be equal to W, which is equal to integral V1 to V2 P dV. Okay. So this we write as a constant into integral V1 to V2 1 upon V to the power of gamma, that is V to the power of minus gamma, okay, dV. So I'll tell you about the constant later, but right now we do it like this, and then we do the normal integration x to the power of n dx is equal to x to the power of n plus 1 divided by n plus 1, provided n plus 1 is not equal to 0. This I have told you several times. So in that case, here it is v to the power of gamma, v to the power of minus gamma, and when we integrate we get v to the power of minus gamma plus 1 divided by minus gamma plus 1. Okay, it's very simple, easy. So which I write as the constant into, because it is minus gamma plus 1, I write it as 1 minus gamma v raised to the power of minus gamma plus 1 v1 to v2, the limits, and I obtain the result constant divided by 1 minus gamma into 1 upon v2, the later limit, gamma power minus 1, and minus 1 upon v1 gamma minus 1. Now I introduce to you the constant. The constant, we know that it was given by P1 V1 to the power of gamma, or P2 V2 raised to the power of gamma, or Pn Vn raised to the power of gamma, and that is the constant which we apply over here. When I put this value intelligently, in the first term I will use it as P2 V2 to the power of gamma for the value of the constant, divided by V2 to the power of gamma minus 1, and because we are intelligent people, so I will write here again the constant value as P1 V1 raised to the power of gamma, here V1 raised to the power of gamma minus 1. So I can write it naturally. How much is that? For example here, okay, V2 raised to the power of gamma, and this will become equal to, when it goes up, V2 raised to the power of 1 minus gamma. So gamma and minus gamma they cancel and it becomes equal to V2. And similarly here it will become equal to V1. So I can write an equation for the work done as equal to 1 over 1 minus gamma P2 V2 minus P1. Okay. Is equal to, I can write as NR, because PV is equal to nRT. So I write it as NR, where N is the number of moles in the system, in the gas. R is the gas constant, universal gas constant. T1 minus T2. Okay. Why T1 minus T2? Because now I shift from 1 minus gamma to gamma minus 1. Because gamma is more than 1, so this has to be positive in the denominator. Okay. And whatever changes has to be done in the numerator. So I obtain the value of W. I can write here, my friend W doesn't want to appear here, but W is equal to NR T1 minus T2 divided by gamma minus 1. And so I can say that if work is done by the gas, let me, even if it doesn't want to come, okay, now it comes there. So I get the equation like this towards the end, and now as the equation speaks, so if the work is done by the gas in the adiabatic process, then this work is greater than 0 or T2 is less than T1. Okay, for W to be positive, this T2 it has to be greater than T1. Okay, otherwise if W is less than 0, then T2 has to be greater than T1. Okay, so this is the adiabatic process, and combined with the isothermal process of expansion and compression, we will talk shortly the adiabatic processes for the expansion and the compression, and we'll talk about the cycle which occurs for that. But before that, I go for the isochoric process. Okay, so besides the isothermal process and the adiabatic process, I have the isochoric process. I think before there was a spelling mistake. I didn't write H with C. Okay, so please correct it yourself. Okay, isochoric process, the volume is constant, or there is no change in the value of the volume. So there is no work is done on or by the gas. So heat absorbed in the process, this entirely changes its internal energy delta, which in turn may change its temperature, and this is determined by Cv, which is the specific heat at constant volume, molar specific heat at constant volume, or specific heat at constant volume, etc., etc. This is a very simple thing. Okay. Isobaric process, delta P is equal to 0, or P is equal to constant. So work done by the gas W is very simple. P, which is the constant, into the change in the volume V2 minus V1, which I can write with the help of the gas equation as NR T2 minus T1. Now, since T changes in this process, isobaric process, the internal energy of the system also changes. So what happens to the heat absorbed? It partly is spent in increasing the internal energy of the system, contributing to the change in the internal energy, and partly to work. So here in this case, what works is the specific heat at constant pressure. The next thing we want to discuss is cyclic process, where the state comes back to its own position. Okay, baby come back. Okay, मेरा पिया घर आया हो राम जी. Okay, so like here, I have plotted the ideal gas PV curves. Okay, So if we start, for example, from here, right, then we have an isotherm and there is an isothermal expansion because the value of V is increasing. Okay. Then in the next process, we come here through an adiabatic process. In the adiabatic process, you can see isothermal process takes place slowly, has to take place. There is an amount of suddenness in the adiabatic process which is happening over here. And then if we want to return, we cannot return this way to the original values of say P1, V1, etc. So what happens is that again we make resort to an isothermal change, and this again the isotherm which we obtain is again is gradual, slow, and the process like I told you. Later on, this is isothermal compression. So expansion, compression, and here it is a kind of an expansion, and here again it is a compression, the adiabatic compression which takes place in the fourth process. So my PR comes back to the home. मेरा पिया घर आयो हो राम जी, baby come back. Okay. Similarly, you could start from any position and with the help of alternate isothermal and adiabatic processes, for example here I compress, then I compress again, adiabatic process, then expand, I come back to this home too. So these are things which are possible. We'll talk about this kind of a, and what is the significance of this area, etc. when we talk to you next in the heat engines and refrigerators and etc. etc. Before in between we'll talk about it, and thereafter we'll talk about the second law of thermodynamics. So look here, because the delta U is equal to 0, there is no change in the value of internal energy. Why? Because internal energy is the state variable. In this comeback process, the total heat absorbed is equal to the work done by the system, is equal to work done by the system. So I have talked to you about the 5 possible processes: the isothermal, the adiabatic, the isochoric, and isobaric, and then of course the cyclic process. And it is with the help of these things that we can talk about heat engines, where the heat is converted into work, or work may produce heat, etc. Okay, there is Carnot cycle. Okay, and there are many other things which are interesting things. I suggest that all these things we are going to discuss, you must come prepared before you open up the next lecture. Go through these things from whatever textbooks you are having, okay, so that you can enjoy. Of course I do enjoy. So thank you very much. See you again.